Hello and welcome to our lesson on matrices and systems. So in the previous topic we talked about matrices just sort of individually and some operations with matrices. What we're going to do today is see how matrices can help us to solve systems, which is where we started with this module. Okay. So first of all, how does a system fit into a matrix? What we're going to do to fit a system into a matrix is basically remove the variables from the system. So the coefficients and the constants from your system are going to go into your matrix, and they'll basically stay in the same order as you see them in the system. We're just going to leave out the variables, and the coefficients and the constants are going to be separated by, instead of equal signs in your system, they're going to be separated by a vertical line. So the vertical line is taking the place of your equal signs. So for example, if we were looking at this system, x plus 2y plus 4 is equals 4, and so on, in a matrix form, if we got rid of the variables and replaced the equal signs with the vertical line, we would have 1x, 2y, 4z, and then 4 here. Let's pretend that's a vertical line. So 1x, 2y, 4z, and 4 here. Or 3, -1, -1, and 10. 3, -1, -1, and 10, and 5, -3, 1, and 1. 5, -3, 1, and 1. Okay? So we're fitting a matrix system into a matrix by removing the variables and replacing the equal signs that separate the variable terms from the constants with a vertical line. And when we do this, this matrix that is resulting here we call an augmented matrix. So it's called an augmented matrix. Okay? And the goal is to solve a system. That's always the goal with the system, is to solve it. Now what we're going to do is get it in what we call upper triangular form. So give me some fancy vocab for a minute. Upper triangular form is a form that's going to allow us to solve using back substitution, but we have to get it into that form. So this is what upper triangular form would look like. The diagonal ones here separate two triangles. Can you see here how we can kind of make a triangle out of these three numbers, and we can make a triangle out of these three numbers here. So in upper triangular form, the upper triangle still contains numbers, but the lower triangle is all zeroed out. Now, why would we want upper triangular form? Well, think about what this means in terms of variables, right? This means 0 x's, 0 y's, and 1 z is equal to 3. If we can get this in upper triangular form, then we can use back substitution to solve. So at this point, we know that 1z is equal to 3, and we could substitute back into the second equation. Since there are only two variables in the second equation, we can see in that second equation that 1y plus 2z has to equal 7. So if y plus 6 has to equal 7, then we know y has to equal 1. And now I could take the y and the z and then plug those both into the third equation, where we have 1x plus 3y minus 5z equal to 8. And so x plus 3 minus 15 equals 8. And x minus 12 equals 8 means we could add the 12 over and say that x is 20. So the goal is to get it into this upper triangular form, which basically means we want zeros along the diagonal. So in this upper triangular form, we want we want ones in the diagonal, and we want zeros below in the triangle below those ones. Okay, so that is upper triangular form. Ones diagonally, zeros below, and then we can use back substitution to solve. Okay. Now, if we wanted to be overachievers, we could solve the entire matrix and get it into what we call reduced row echelon form. I know this is some fancy terminology, and I don't want you to get hung up on the terminology, but if you're moving on to higher levels of math, like a linear algebra class, you're going to see a lot of this. So this would be a completely solved matrix. This says 1z equals 2, 1y is going to equal -3, and 1x is going to equal 5. And we could use a series of operations to get it into this form. So this one is called reduced row echelon form. Reduced row echelon form. And if you ever solved a system like this using a TI calculator, part of the solving process in the TI calculator requires you to press this RREF button at the end to actually solve, and that's because it's putting the system in reduced row echelon form. That's what that RREF stands for. Again, I'm not so hung up that you get I'm not so concerned with the technology. I don't want you to get hung up on that technology. But I do want you to be familiar with, or at least have these words on your radar. Okay, so this reduced row echelon form just means that the matrix is completely solved. But how do we go about solving? So using the matrix to solve is really no different than using elimination to solve. We're just doing the process without the variables. In the same way, synthetic division does the same thing long division does with polynomials, just does it without the variables to simplify. That's sort of the idea here, is we're trying to solve the system using elimination, but without having to deal with the variables, just dealing with the numbers, okay? The number piece of it. So there are 3 rules. If we're going to solve a system in a matrix, there are 3 ways to take your augmented matrix and change it so that we get it into that upper triangular form so we can use back substitution to solve. Now the 3 rules are the same 3 things that we are allowed to do with elimination. So let me, I'll give you one at a time. So first, rows can be switched. That means that we can just move, when I say rows, that's what they are in your matrix, but these rows actually are equations. We can just move the equations around. So for instance, let's say we had a system like 3x plus y equals 5 and 2x minus y equals 8. If I wanted to, I could take the second equation and put it on top of the first one. I haven't changed a thing. It's the exact same system. I just relocated that first equation, or the second equation, and made it first. That's doable here. That is a legal move here. So if I wanted to, in a matrix, take an entire row and move it, I could absolutely do that. Okay, so that's one of the rules. And rows can be multiplied is the second rule. Rows can be multiplied by any number but 0. Again, we do this with elimination. Okay, so let's say, for example, let me give you a new system here. Let's say we had 4x minus y equal to 3, and then 5x plus 3y equal to 7. Just making up numbers here. If I wanted to eliminate the y's, I could multiply this entire equation by 3. That would make it 12x and minus 3y equal to 9. And that would help me go through that elimination process, right? It's the same thing with a matrix. I can take an equation and multiply it by any number but 0. I could also divide it by a number if I wanted to, because it's the same. So for instance, 4x, let's say plus 8y equals 9, and then let's say we had x plus 2, no, let's go minus 2y equals 1. Instead of multiplying this equation by 4, maybe I want to divide, the first equation by 4. So if I took this one and multiplied it by a fourth, or divided by 4, same thing, I'd get 1x, and I would have 2y, and then an ugly fraction over here, but it's a doable thing, okay? So we are allowed to do that with matrices as well. We can multiply by a non-zero number. And then the last one sounds the worst, but it's the one that we probably use the most. You can change a row by adding a multiple of another row to it. So change a row by adding the multiple of another row to it. So what we're doing is, I'm making a mess here. Okay, 2x plus 3y equals 1, x minus, let's go, y equals 4. If I wanted to change my circumstance here, let's say I multiplied this equation by 3, it would give me 3x and negative 3y and 12, and now I could add these two together to give me a new 5x equal to 13. And that new equation we would see as a new row in our matrix, okay? So it's the same thing that we do with elimination, it's just without the variables, and the idea is to simplify the process, but because it's foreign to us, sometimes we tend to resist, okay, and not want to use this process. Now, I would say for a 2x2 system, just using substitution or elimination is pretty nice. And even for a 3x3, elimination isn't so bad. But again, the farther you go in math and the bigger systems you're dealing with, the more complicated the variables become. So it's in those larger systems where this organizational thing, this matrix concept, is more useful. Okay? So we're going to look at this because for the purposes of this class, we need some exposure to this concept. But really, it's better suited for larger systems, okay? Now, the goal is to, again, get our matrix into upper triangular form. So what we want is a 1, a 1, and a 1 in our diagonals, and we want zeros below. So 1, 0, 0, 1, 0, 1. And the order we're going to do is we're going to start in row 1. Okay, so we're going to start by getting this 1 here, and then we're going to work down from there. So start at the top of row 1 and work down. So the first thing we're going to do is, again, we're going to get this 1, and then the second thing we're going to do is get this 0, and then the third thing we're going to do is get that 0. Then we'll go on to the next consecutive row and work down from there. Or actually, this should be next consecutive column. So we start in column 1, work down, and then we're going to start in column 2, get this 1, and work down from there. So this 1 would be the 4th piece, this 0 would be the 5th piece, and then the last thing we're going to do is get this 1 here. So the goal is to go in this order: 1, 0, 0, 1, 0, and 1, so that we can get that upper triangular form. Okay? Now just, oops, I didn't mean to delete that. This, let's say column, that word fits there a little bit better. These 3 rules, just to kind of help us along, the switching of rows is generally only going to be done in the very first step, if it's done at all. So this is first step, maybe. Okay, maybe in the first step or not at all. If it's used in the first step. Usually used once in the first step, okay? Not generally used after that. The multiplying by a non-zero number, this is generally the rule that we're going to use to get a 1. Use to get 1s. So if I want a 1, a 0, a 0, a 1, a 0, and a 1, these guys, this 1 here, this 1 here, and this 1 here, if we can't get them by just switching, generally it's going to be multiplying by some non-zero number or dividing by some non-zero number. Okay? And then the adding a multiple of a row to another, that's going to be the rule that we're going to use to get zeros. So we're going to use this to get our zeros. Okay? And then once the matrix is in our correct form, just as we saw in the triangular form in the previous part here, so once we get it to look like this, it's just back substitution. So back substitution once we get it in our upper triangular form. And honestly, it doesn't even have to be in completely upper triangular form. So 1, 0, 0 is a must. 1, 0 is a must. But if we don't get a 1 here, if we just have some number and then another number here, any number left here is going to be fine because we can just divide to solve. So the thing is, we want to be able to use that back substitution. But the 1, this 0, this 0, this 1, and this 0, that's a must, okay, in order for this process using matrices to work. So let's try this. Are you ready? So let me put this first into an augmented matrix. So if I put this into an augmented matrix, I'm going to have 5, 2, and 11, and then 1, 1, and 4. Okay, now for a 2 by 2, my goal is to get a 1 here, a 0 here, and a 1 here. The number that's here won't matter. If I can get this 1, this 0, and this 1, and I'd have some number here, then I can solve for y, plug back in, use back substitution to solve for x. So the goal with a 2 by 2 is, here, let's put that over here. The goal is to get the 1, the 0, and the 1. Okay? So the first thing I can do in this matrix is I can get a 1 pretty easily in this first spot if I just move this equation. Now, if you saw that up front and you wrote it that way, awesome, one less step to take. But all I'm going to do is switch row 1 and row 2. So I'm going to swap out our rows. So I'm going to row 1 and row 2. I'm going to switch them, and I like to write what I'm doing just so I can go back and try to follow my work if I made a mistake somewhere. So row 1 and row 2, I'm just going to swap those out. Okay, now you don't have to show all your work like that, but again, if you are doing this with a larger system, it's going to be really helpful, and I think the organization is the key to a lot of the work that we do. So I'm going to put 1, 1, and 4 first. And then I'm going to put the 5, 2, and 11 next. Okay, so just flip-flop the rows, just like moving in one entire equation above the other, no big deal. So I got this part of my goal, the 1, check, done. Now I need to get the 0 that is below the 1. So how can I make the 5 a 0? Well, I can't switch the rows to make that happen. I can't multiply it by anything because what I'm allowed to multiply by is anything but 0. So I can't multiply to make it 0, which means I have to use the third row. I have to add a multiple of another row to it. Okay? So what would you have to add to 5 to make it 0? You would have to add negative 5. And I can make this a negative 5 by multiplying it. If I do negative 5 times 1, I get negative 5, right? So I'm going to take negative 5, multiply row 1, and add it to row 2. So I'm adding a multiple of the first row to the second row. So let me write down what I'm doing. Okay. I'm going to do, the work here is negative 5 times row 1 is going to be added to row 2. Negative 5 times row 1 is going to be added to row 2. So then I end up with, if I do negative 5 times row 1, let me just do the work here. Normally would, as you get better with this, some of this you can do in your head. But negative 5 times row 1 would be negative 5, and 4. If I added that to row 2, which was 5, 2, and 11, I'm going to get my new row 2, okay? So what's happening here is row 1's not technically changing. I'm just using a multiple of it to change row 2. So row 1's not changing, but if I do negative 5 times row 1 and add it to row 2, that is to get a new row 2. So my new row 2 becomes a 0, a negative 3, and a 15. So I'm going to get 0, negative 3, and 15 here. And basically I'm done, but I'm going to go one more step just so you can see all the rules in play. If I got my 1 and then my 0, my last step would be to get a 1 there. So what can I do to make the negative 3 a 1? Well, I don't want to flip-flop the rows because that's going to mess up my first column. But I can divide it by a negative 3, which is the same as multiplying it by a negative 1/3 to make it a 1. So I will use the second rule there. That's the one I'm going to use to get my 1s. And so let me get rid of those. Okay, so I'm going to do row 2 divided by a negative 3, which is the same thing as multiplying it by negative 1/3. And so that's going to get me not anything different for row 1. The whole purpose here was to move to the next row. If I divide 0 by negative 3, I still have 0. Negative 3 divided by negative 3 gets me the 1 that I was trying to get, and 15 divided by negative 3 puts a negative 5 here. And now I'm basically solved, okay? At this step, I know that y has to equal -5. And then if I plug into the previous equation, if I plug into this previous equation, I know that 1x plus my 1y has to equal 4, which means x has to equal 9. And so my solution would be 9 and -5. So my solution is at 9 and -5. Okay? So again, foreign, probably weird to do this. Maybe you're thinking substitution or elimination would be so much easier. And at this point, you're probably right, because those are things you've done before and you're comfortable with, and this is a small system and it's not hard to use those other processes. But again, this is breaking you into this idea, and really it's more useful as you deal with larger systems. And it's like anything else. If you were to use this method a bunch of times, you would get really good at it. You could save some of the work off to the side, and you might like the process, okay? Let's try another one. I'm going to try another 2 by 2 here. And swapping the first and second rows in this case is not going to do anything for me here, so I'm going to just put my augmented matrix for -3 and 5, 7, 2, and 16. And the goal, remember for a 2 by 2, my goal is to get a 1 and then a 0 and then a 1 in that order. So I can't swap rows to make a 1, which means I'm going to have to multiply or divide to make a 1. So what I'm going to do is I'm going to do, I would divide this by 4 to make it a 1. So I'm going to take row 1 and divide it by 4. Okay, row 1 gets divided by 4. And that's going to give me, I want to make sure I have space, 4 divided by 4 is going to be 1. -3 divided by 4 is going to be -3/4. And then 5 divided by 4 is going to be 5/4. Okay? And then I didn't change row 2, so that's still a 7 and a 2 and a 16. So now I need to get a 0. So right here, I need to have a 0. Well, I can't multiply to make it 0. Swapping the rows, only going to use that in the very first step and then probably never again. So what I want to do to get a 1 is add a multiple of another row. So I have to add -7 to 7 to make it be 0, and I could make this a -7 by multiplying it by a -7. So I'm going to, in this next step, do -7 times row 1, and I'm going to add that to row 2 to make my new row 2. Okay, so it's not going to change row 1. The goal was to change row 2 by adding a multiple of another row to it. So I'm not changing the 1, the -3/4, or the 5/4. Okay, I'm just changing row 2. And just so you can see the work, if I did -7 times row 1, -7 times 1 would be -7. -7 times -3/4 is going to be 21/4. And then -7 times 5/4 would be -35/4. And then row 2 was 7, 2, and 16. So that would give me my new row 2, which would be 0. That's what I wanted. And then 21/4 and 2, just so I don't do anything silly, 21/4 plus 2 is 7.25, or as a fraction, 29/4. And I like the fractions better, so I'm going to make that 29/4. And then -35/4 plus 16 is going to get me 7.25, so again, 29/4. So 29/4. So I end up with 0, 29/4, and 29/4. And just to complete the process here, I'm going to go ahead and get my last one, although I can see the answer at this point, and if you could too, that's totally fine. I'm going to go ahead and multiply the second row by 4/29 to make a 1 right here. So I'm going to do 4/29 times row 2. So 4/29 times row 2 is, again, to change row 2. Doesn't change my 1, -3/4, or 5/4. But 0 times 4/29 is 0. 29/4 times 4/29 is going to be 1, and then the same thing here, and now I'm basically done. So this right here tells me that y is going to equal 1, and then I'm going to plug that in. I'm going to plug that in to figure out my solution for x. So 1x minus 3/4 y has to equal 5/4. So x minus 3/4 equals 5/4. If I add that 3/4 over, I get 8/4, which is 2. So now I know my solution using matrices is 2 and 1. And again, not the easiest method to solve. Clearly, it would be easier to throw this into Desmos and see that these two lines are crossing at 2, 1, but it is an option, and the larger the systems get, the better this option becomes. Okay? Now, the real bear. You ready for this? Pause, go get a drink, take a stretch break, because this is going to be a doozy. No, it's not that bad. We're going to try to solve a 3x3, and the goal for the 3x3 is to get the 1, the 0, the 0, the next 1 and 0, and then the last 1. So in augmented form, I already start with the 1, which is perfect. So 1, -2, 3, and 3, and then 2, 1, 5, and 8, and then 3, -1, -3, and -22. Sometimes just getting it written correctly is half the battle. So there it is. I already got the 1. So my first step is really to get a 0 right there. And I would have to add -2 to it to get 0. The only way to add -2 to it is to use a multiple of another row. So I'm going to do, in my first step here, -2 times row 1, and add that to row 2 to change row 2. Okay? So I'm changing row 2. I'm not changing row 1. So row 1 is going to come over here. I'm not changing row 3. So that's going to come over as well. All I'm changing is row 2 by adding a multiple of row 1 to it. So this is -2 times row 1 would be -2, 4, -6, and -6. Row 2 is 2, 1, 5, and 8 right now, but once I put these together, I get my new row 2, which is 0, 5, -1, and 2. So 0, 5, -1, and 2. Okay? So the next is the 0, where the 3 is at, right here. So right here, I need to get a 0. And I'm going to do the same thing I did to get my last 0. I'm going to use a multiple of row 1. So I'm going to this time multiply -3 times row 1 and add it to row 3. So this doesn't change row 1. 1, -2, 3. It doesn't change row 2. 0, 5, -1, and 2. It's just giving me a new row 3. I'm getting a new row 3 by adding a multiple of row 1 to it. So we've got -3 times row 1 would be -3, 6, -9, and -9. Row 3 was 3, -1, -3, and -22. But now when I put these together, I get my new row 3, which is 0, 5, -12, and -31. So now I'm bringing over 0, 5, -12, and -31. All right, so I've got this part of the goal. Now I've got to get the 1 in that next spot. Okay? So how do I make a 1? Making a 1 is where we multiply or divide a row. So my next step would be to do row 2 divided by 5, or multiplied by a fifth. It's the same thing. And because I'm out of space, I'm going to pick this up over here. And some people prefer to work vertically. It doesn't matter how you want to organize. If you want to work down with your matrices, you're going to probably end up running out of space that way too. All right, so row 2 divided by 5 doesn't change row 1. So row 1 is still, actually, let me make this go a little further. Okay, row 1 is still 1, negative 2, 3, and 3. Row 3 is still 0, 5, negative 12, and negative 31. I'm just dividing row 2 by 5 to get the 1 that I need here. So 0 divided by, so I'm dividing row 2 by 5. 0 divided by 5 is still 0. 5 divided by 5 is 1. That's what I needed there. Negative 1 divided by 5 is negative 1/5. And 2 divided by 5 is 2/5. Okay? So we're almost there. I've got 1, 0, 0, 1. Now I need to get that 0. So how do I get that 0? Well, now I'm going to add a multiple of row 2 to row 3. If I do negative 5 times row 2 and add it to row 3, then that negative 5 and 5 will get me the 0 here, and it won't mess up the zeros that I have already established in column 1. Okay? Made dots everywhere. So negative 5 times row 2 plus row 3 does not change row 1 or row 2. It's just giving me a new row 3. So I'm going to carry over my 1, negative 2, 3, and 3. And I'm going to carry over my 0, 1, negative 1/5, and 2/5. I'm just changing row 3. Okay? So how's it going to look? Well, negative 5 times row 2, up a little bit. Negative 5 times row 2 would, so I'm multiplying here by negative 5. That's going to give me 0, negative 5. Negative 5 times negative 1/5 is going to be 1. And negative 5 times 2/5 is going to be negative 2. And then I'm adding row 3, which was 0, 5, negative 12, and negative 31. And that's going to get me my new row 3. And I'm so squeezed for space here. I can only imagine that you are also squeezed for space. Okay, so now my new row 3 is 0, 0, negative 11, and negative 33. Okay, so 0, 0, negative 11, and negative 33. And one last step just to complete the upper triangular form, although I can see the answer from here, so if you wanted to stop, that would be fine. Actually, I'm gonna go ahead and stop there, but if you wanted to continue, you would just take row 3 and divide it by a negative 11, and that would put a 1 here, and that would give you your solution there. But honestly, now that we've gotten this far, we can see right here that if negative 11z equals negative 33, that z has to equal 3. So now I'm going to plug that into this second equation. So I have 1y minus 1/5 times z has to equal 2/5. So y minus 3/5 equals 2/5. If I add that 3/5 over, I get 5/5, which means y has to equal 1. Now I'm going to take the z and the y and plug into my last equation. So those are both going to go into the first one there. Actually, my first equation, not my last. The last one that's left for me there. To show me, let's see, 1x minus 2y plus 3z equals 3. So x minus 2 plus 9 equals 3. That's x plus 7 equals 3. If I subtract the 7 over, then x has to equal negative 4. So I have my solution. My solution, which is x, y, and z, so negative 4, 1, and 3. And that could be verified with Desmos, and you're probably still thinking that that is the easier way to solve. But I kind of like this method, and when I took linear algebra and was solving a 6x6 system, this method of using matrices to solve was much more efficient. And again, the work that I'm showing there in green, if that's stuff you can do in your head, cool. But I would still probably write down the operations just so you don't lose yourself. but it's exposure, okay? If you like the process, cool, use it. If not, ultimately you're going to be able to choose which way you solve, okay? But again, it is good exposure, and if you're going to move on, you're going to see these things again. So by all means, verify what you're doing with Desmos, but you should absolutely be trying this because it is a skill that will be useful later. And yeah, hopefully I've given you enough to get started on your practice. But as always, if you need some extra help, then just reach out. All right, guys, take care.